Okay, so today we're going to focus on some more torque examples, at least in this video. So the first one, 1A, is actually very similar to the last example that you guys did. A 5-meter long, 30 kilogram seesaw has adjustable seats that can be slid forward or backward to accommodate different users. It is pivoted about its center of mass. A 25 kilogram child sits at one end of the seesaw. A. Where must a 500 Newton force be applied in order to hold the seesaw with the child horizontal in the air? Very first thing you're going to do, you realize that a seesaw is going to pivot up and down, or it can turn and rotate, it can spin. This is not a linear, not necessarily a linear force equilibrium question. This is a rotational equilibrium question. So that means we're not just going to draw a dot, we have to draw out the entire object and everything that's acting on it. So let's do that first. Here is my seesaw. Okay, it's pivoted in the middle, so I'm going to draw my fulcrum here. Okay, and let's see here. We are told that there is a 25 kilogram child at one end of the seesaw. I'm going to show that by drawing a box, 25 kilograms. Okay, and we want to know where to put a 500 Newton force, presumably on this side, so that everything stays balanced. Let's go ahead and let's write down the forces that are acting, but before we write the forces, let's draw in our axis of rotation. Now, very clearly here, this is going to be another simple case. Let's put the axis of rotation where it actually is, right at the center of this problem, okay? Axis of rotation. Now we can deal with the forces. First of all, the seesaw itself is balanced right here. That must mean something is supporting it. There must be a normal force up like this. In addition, at the axis of rotation, we put the axis of rotation right in the middle of the seesaw. That's actually also where the center of mass is. So I'm going to draw, and as we know, the force of gravity acts from the center of mass of an object. So what I'm going to do is I'm going to draw a force downward. This is going to be the force of gravity from the board, FGB, B for board. The 25 Newton, or the 25 kilogram child over here, he also exerts a force on our seesaw. I'm going to call that FG, well, I'll call it 1, I suppose. And I've also got the force over here, this unknown force, or the force F over here. We're just not really sure where that goes on here. Where must a 500 Newton force be applied in order to hold the seesaw with the child horizontal in the air? So, I've got my forces. What I need to do now is write out my net torque equation, because these forces are not causing it to move linearly, they're causing it to spin. So I have T net. And one of the things I can actually do, I'm going to do this a little differently than I did before. Last time I wrote all the torques out here, then I saw which ones were 0, then I canceled them out, and then I calculated here. Another option that you have is to calculate all the torques off to the side at first. So take each force and calculate the torque from those forces. So I could calculate the torque from, let's just go left to right, FG1. So I'm going to do torque 1 equals R1 F1 times sine theta 1. Okay, let's start with the sine theta part. Sine theta, or actually no, let's just go left to right. R1 is the distance from the displacement from the axis of rotation to where the force acts. Axis of rotation in the middle of the board, force acts at the end. Board is 5 meters long in total. That must mean that R for this force is 2.5 meters. The force acts 2.5 meters away from the axis of rotation. F1 is equal to the weight of the child, which is just mg. The child has a mass of 25 kilograms times 10 meters per second squared. F1 must be 250 newtons. Sine theta 1. Sine theta 1 is the angle between the r vector, the displacement vector that goes out this way, and the force, which goes straight down. If they were drawn tail to tail, that would look like this. That's clearly a 90-degree angle. Sine of theta 1 is 1. Torque from 1 is 2.5 times 250, which is 625 Newton meters. Let's find the torque from the normal force. This ends up being really easy. The displacement of the normal force from the axis of rotation is 0. The normal force acts directly on the point where the axis of rotation is. So R is 0. So the torque from the normal force is also 0. Similarly, the torque from the force of gravity on the board is also going to be 0. You'll notice that I'm just writing down all the little subscripts so I keep everything straight in my head. Again, this force of gravity acts directly at the axis of rotation. That doesn't cause a twisting or turning. Again, it's kind of like trying to open a door by pushing on the hinges. It's never going to work. That's 0. Therefore, the torque from the board is 0 Newton meters. Now, finally, I'm going to do one more. I'm just going to put it up here because I know I'm kind of running out of room here. Let's see. We need the torque from that force. Okay. Torque from that unknown, the force of 500. We don't know the R for that. Matter of fact, that's what we're looking for, okay? But we do know that someone is pressing straight down onto the seesaw, and we know that the R would be going straight out to it. Again, that would be a right angle, so this would be 0, or 1, excuse me, sine of 90 is 1, and we know that F is 500. So we know that that torque is equal to 500 times whatever the length of that displacement vector is. So now that I've got all of these done, all these torques calculated individually, now I'm going to finish writing my net torque equation. I'm not even going to include the torques that are 0. I'm just going to include the torques that are non-zero. Okay, clearly this one is non-zero, and 625 also very clearly non-zero. So using the convention that counterclockwise is positive, Fg1, the force of gravity from the 25 kilogram kid, if we were to, here, let me do that. If we were to take this and pretend we could like grab it like a piece of string and pull this around and pull the system, that would cause the system to rotate in a counterclockwise manner. So Fg1, the torque from 1, must be a positive force, or a positive torque. Likewise, oh man, I scratched my paper up. Likewise, the force here, the unknown, the force that we don't know where it goes, that force is also going to give you a, well, not also, that force is going to give you a clockwise rotation. If you just had that force, it would cause the system to rotate this way. That's clockwise. That force must be negative, or torque, excuse me, must be negative, equals I alpha. Now, the thing about I alpha is we want to keep this horizontal in the air. We want to keep this balanced, no change to the rotation. It's not rotating now. We don't want it to rotate in the future. That means the angular acceleration is 0, which means that my two torques must be equal to one another. T1 we found was 625 Newton meters. TF we found was 500 times RF. We divide both sides by 500. And we end up with 1.25 meters is RF. So, here's what this means. Remember, R is the displacement vector from the axis of rotation to where the force is applied. This means that the force is applied 1.25 meters. We know it has to be on this side from the axis of rotation. We need to specify where exactly this is, okay? Because 1.25 meters could be either here or here. Since we know it's over here, let's say how far this is from this side. If RF is 1.25 meters from the axis of rotation, then this force is applied 2.5 meters, because that's half the board, plus another 1.25, 3.75 meters from the left edge. Very, very similar to the last problem. Okay? Now what we're going to do is we're going to talk about the normal force. There's actually two different ways you can find this. I'm going to show you both. Okay. The first, you could actually do this question simply by using old-fashioned net force equation. Because watch this. In the y direction, there are four forces here. I suppose I should put a little axis there. X, y. That direction is positive rotation. F net y equals Fn minus Fg1 minus Fgb minus the force, the 500 newtons, equals MAY. This seesaw isn't accelerating down, it's not accelerating up, it's staying in place. The acceleration in the y direction must be 0. If we want to solve for the normal force, the upward normal force must just be equal to the sum of all these downward forces. So m1g plus the mass of the board times g plus F. m1 is 25 kilograms, 10 meters per second squared. The mass of the board is 30 kilograms times 10 meters per second squared plus 500 Newton force pushing down. That means Fn is equal to 250 plus 300 plus 500. The normal force must be 1,050 newtons. There you go. But I did say there was another way to solve this. You can also solve this using rotational equilibrium. And the key here is that this is in rotational equilibrium. If that is the case, then since in rotational equilibrium, we can set our axis of rotation to be anywhere, and the problem will still work.